This is the lecture 8 of the course MTH305A. So today's topic is implicit function theorem. So topic is implicit function theorem. Implicit function theorem. So first we give some motivation, then we will state the theorem statement, then finally proof of the theorem. So let us start with motivation. So as a part of motivation, we consider two examples. So here this is example 1. Okay. So suppose x and y are real numbers and consider the relation between x and y given by x square plus y square equal to 1. So consider the relation between x and y, where x and y these are reals. X square plus y square equal to 1. So we label this as equation 1. Then equation 1 is equivalent to f of x comma y equal to x square plus y square minus 1, and this is equal to 0. Okay, so this is basically equation of a circle with center at 0, 0 comma 0 origin, and radius 1. So this is R2, here it is y axis and this is x axis, and this is the circle. Okay, so this is basically the set of all points x comma y in R2 such that f of x comma y equal to 0. Okay, so now note that y equal to plus minus square root of 1 minus x square. So here we have two equations, y equal to plus square root of 1 minus x square, and y equal to minus square root of 1 minus x square. So these equations, these are explicit functions. Again, so these are relation between x and y. So these equations give equivalent relation between x and y as in equation 1. Okay, equivalent relation between x and y as in as in equation 1. And moreover, this is true near every point so near every point in this set except at plus minus 1 comma 0. So what does it mean by near every point? So near every point means if more precisely, if x naught comma y naught belongs to the set x comma y such that f of x comma y this is equal to 0, then so and x naught y naught not equal to plus minus 1 comma 0, then there exists epsilon greater than 0 and a function in function y in x, y of x equal to square root 1 minus x square for all x belongs to x naught minus epsilon, x naught plus epsilon. So here we are considering y naught is greater than 0. So suppose this is the point x naught comma y naught, where y naught greater than 0, then here it is x naught, then there exists an open interval epsilon neighborhood of x naught such that and function yx equal to 1 minus x square for all x belongs to on this epsilon interval x naught minus epsilon x naught plus epsilon. Then suppose here it is x belongs to this interval, then we have so this is x naught and this is y naught. And if this is x, then we have get some y of x here, so that x comma yx belongs to this set, that is so that f of x comma y x equal to 0. Okay. So now we move to example 2. So well, let us mark the page number. This is page 1 and this is page 2. So here we consider the relation between x and y. Consider the relation between x and y given by x comma y. This is equal to y power 5 plus y power cube plus y plus x, and this is equal to 0. So we label this equation by 2. Then from equation 2, it is straightforward to say that we can solve x in terms of y. So we can get a solution for x as a function of y, as a function of y, namely, so let us denote the function by g of y, and this is equal to x, which is equal to minus y power 5 plus y cube plus y, such that f of, so replace x by g y, comma y, this is equal to 0. Okay, so for every y we have gy such that f of gy comma y, this is equal to 0. Okay, so here we have a question, can we write y as a function of x, so maybe explicitly like y equal to let's say h of x, such that f x comma h of x equal to 0. If so in such a case hx should be the solution. So in such a situation, h of x must be a solution of the equation 2. Okay, solution of equation 2 for y in terms of x, but in general there is no formula for finding. So in general there is no formula for finding roots of a polynomial of degree greater than or equal to 5. So there exists no uh, formula for finding roots of polynomial of degree greater than or equal to 5. But in this example at least we can guarantee the existence. So for every fixed x naught, let us uh, define a function phi of y, this is equal to y power 5 plus y power cube plus y plus x naught is fixed. So this implies the derivative of phi, uh, this is the ordinary derivative of phi, this is equal to so this is equal to 5 times y power 4 plus 3 times y power 2 plus 1. So for every real number y, so the first term is greater than or equal to 0, and second term is also greater than or equal to 0, and third term is 1. So this is always greater than or equal to 1, and so this is always greater than strictly greater than 0. That is why p is increasing. monotonically increasing, and this is strictly increasing, strictly. And also note that limit y tends to plus infinity, phi of y, this is equal to this plus infinity for every fixed x not real number, and limit uh, y tends to minus infinity, uh, phi of y, this is equal to minus infinity. Okay, therefore from intermediate value theorem, we have there exists a there exists a zero of the function phi. So this is page 3. So by intermediate value theorem, there exists some real number y not such that phi y not equal to 0. Okay, thus we have so for given every x naught, this guarantees existence of a function h of um, x, for given every x, and there exists some hx uh, mm, such that phi of hx equal to 0. Thus we have there exists a function h of x for given x h of x such that uh, f of x comma hx, this is equal to 0. So here we have only existence of existence of such a function hx. So here we only have the existence of such a function hx, such that f x comma h of x, this is equal to 0. But no explicit formula of h of x. So we don't have any explicit expression for hx. So at this point, so in the first example we have explicit formula, um, y equal to square root of plus minus square root of 1 minus x square, but here we don't have the expression for h of x. Okay, so at this point we have the following natural question. We have following natural question. So this is question 1. When a relationship f x comma y equal to 0 can be equivalently written as y equal to f of x locally. So locally means so consider the first example. So for example, when So this is example. So when f of x comma y, this is equal to x square plus y square minus 1. Suppose here, so we consider x naught y naught, a point in R2 such that f of x naught y naught is equal to 0. This is x axis, this is y axis. So consider y naught is greater than 0. So uh, so here we have the point x naught, and so this is point y naught. So locally means if x naught y naught is a point where uh, f of x naught comma y naught is equal to 0. So does there exist some epsilon neighborhood, uh, x naught minus epsilon, x naught plus epsilon. So this is the neighborhood. And a function, um, let's say, so here we have denoted by f. So a function f from this epsilon neighborhood to set of reals such that for x belongs to the interval x naught minus epsilon, x naught plus epsilon. So we get some point f of x near the point y naught. So suppose here this is f of x. So well, suppose this is point x, and then there exists f of x point over here, such that x comma f of x, so f of x comma f of x, this is equal to 0, and f of x should be near y naught. Okay, so that is, this is the point x comma f of x. So this is the meaning of locally. So here note that f is a function from r cross r to r. So big F, this is function from r to r. More generally, we ask the question below. So instead of r here, we may consider, so question 2, we may consider some Rn, if Rn cross r to r. Let this is a function with f of a1 and so on an. This is point in Rn, comma some b, b is real, or this is equal to 0. Then the question is, when can we find for each x1 and so on xn in Rn near a1 and so on an, near the point a1 and so on an, a unique point y near b, such that f of x1 and so on xn comma y, this is equal to 0. Okay, so this is a more general question. So in question 2, if you put n equal to 1, then this question coincide with question 1. Okay, so let us move to the next page, page number 4. So the general question is, question 3. Let f is function from Rn cross Rm to R be a function with, so this is, let us take, this is capital F, with f a comma b equal to 0, where a in R n, b in R m, that is a comma b belongs to R n comma R n cross R m. Okay. Well, so therefore the question is, can we find for each, so let me draw a picture. This is Rn, this is Rm. So here we have a comma b, so this is a and this is b. So can we find for each x near a, so suppose here this is the point x, so can we find for each x near a unique point y near b, so this is b, so some point near y near b such that f of x comma y this is equal to 0. So if so for given x there exists a point y near b, so we can denote it y is a function of x. Okay, or maybe y equal to small x of small f of x, that is f x comma f of x, this is equal to 0. So this is the general question. So answer of these questions 1 to 3. So note that when m equal to, so here sorry this is m. So when in question 3 when m equal to 1, question 3 coincides with question 2, and when m equal to 1 and n equal to 1, then question 3 coincides with question number 1. Okay, so answer of these questions is implicit function theorem. Implicit function theorem. So note that, so implicit function theorem gives only the existence of such a function f x, little f x. So this answers only the existence, but no explicit formula in general, in general. Okay, and so let us state the theorem. Okay, so we move to the next page, page number 5. Page 5, statement. Theorem, implicit function theorem. So we state the general version. Let f is a function from Rn cross Rm to Rm, so be a C1 function. So what is C1 function? C1 means continuously differentiable function. So all the partial derivatives, so they exist and continuous. Okay, so C1 means continuously differentiable function on an open neighborhood of A comma B belongs to Rn cross Rm. So A belongs to Rn and B belongs to Rm, and at the point A comma B, so well, let me denote this function by uh, capital F for the consistency uh, of notation, and f of A comma B, this is equal to 0. Okay. Also let M be the matrix of order M cross M given by the n plus jth partial derivative of ith component function of f at A comma B. Okay, so j runs through 1 to m and I runs through 1 to m. Therefore this is a matrix of order m cross n. So m is the matrix given by this expression. So now if determinant of m is not equal to 0, then there exists an open set, set U in R n containing the point A and an open set V in R m containing the point B with the following properties. So property 1. So the first item is f of x comma little f of x. This is equal to 0, and that is so suppose this is Rn, this is Rm. So here we have point A and here we have point B, so that this is the point AB with f of A comma B equal to 0. Okay, So this is the point f of a comma b equal to 0, and here this is uh, u, and here we have v, open neighborhood of b. So for a point here x, we get some point here and denoted by f of x. Okay, so that f of x comma little f of x, this is equal to 0, and furthermore if this is a function from so let me rewrite the uh, first item. So f of okay, let me rewrite the items. The first item is following: for each x in u, there exists f of x belongs to v such that f of x comma f of x, this is equal to 0, and moreover, so f is a function for from u to v. Okay, so this is differentiable. Okay, so this is the statement. The statement is somewhat complicated, but the proof is simple. The proof uses not the proof uses inverse function theorem. Inverse function theorem. So you may recall the inverse function theorem. So now we prove this theorem. So this is page number 6. Proof of implicit function theorem. So we define a function, a script f, from R n cross R m to R n cross R m by script f of x comma y. So x belongs to Rn and y belongs to Rm. This is equal to x comma capital F x comma y. Okay, and then f prime of a b, this is invertible because determinant of this equal to determinant of m. Okay, so basically this is the Jacobian matrix of script f prime of a b. This is equal to block matrix. So here we have identity matrix of order n cross n, and here we have m. So it does not matter what we have here, and this is 0. So this is block matrix, and determinant of this equal to determinant of m, and this is not equal to 0. Okay, so apply inverse function theorem. So inverse function theorem says that there exists open set U cross V open in R n cross R M containing the point A comma B and and some open set W open in R n cross R M containing the point script F A comma B, and well, this is equal to uh, A comma capital F A comma B. Okay, so there are such open subsets of Rn cross Rm such that the restricted function f restricted on U cross V to W is invertible with C1 inverse. Okay, so C1 inverse means continuously differentiable. Let me write here, note it here. Continuously differentiable. So these are the points. First we define a function, then in the next step we apply inverse function theorem. Now suppose H is the inverse W to U cross V, inverse of so this is basically script F. Okay, this is script F. So suppose this H capital H is the inverse of the function. So this function, then H of x comma y, so basically x is in, so this is a subset of Rn cross Rm. So the points in W, a generic point in W looks like x comma y, so x is in Rn and y is in Rm. So h of x comma y, this should be uh, this should be of the form x comma k x y. Okay, where for some k, this is from W to V. Okay, so k x y, this is in V. So and hx the function h is c1, so k is c1 function, and x comma y, this maps to k x comma y, that is in V. Now in the next step, so let us move to page number 7. Now we consider projection map from R n cross R m to r m defined by so let this be defined by pi of x comma y, this is equal to y. Then what we have, script f of x comma kx of y. No, so f of x comma kx comma y, this is equal to, so this is equal to f composed with h x comma y. So because h of x comma y, this is equal to, so h of x comma y equal to x comma kx y. So x comma k x comma y equal to h of x comma y, and this is capital F. Okay, and so this is equal to x comma k x y, and capital F, this is equal to script f. So note that script f equal to x comma capital F x comma y, and so so this is, so note that this is equal to x comma capital X y, and this implies pi composed with script f x comma y, this is equal to f of x comma y. So pi composed with script f equal to capital F. So we replace this capital F by pi composed with um, script f composed with h of x comma y, and composition of mapping is associative, so this is equal to pi composed with, then uh, script f composed with h, okay, of x comma y, and they are inverse to each other, so this is equal to pi of x comma y, and this is equal to y. Therefore if x comma k x 0, this is equal to 0. Now go back to the statement of the theorem. Now we define f of x equal to k x comma 0. So this is C1 function. Okay, then we have f of x comma small f of x, this is equal to 0. Okay, so this completes the proof. Okay, so here we stop this lecture. Thank you very much.